As an example of using continuity, let's look at a theorem that's very useful in solving equations. So the theorem is called the intermediate value theorem, and the statement of the theorem is a bit of a mouthful. It says if f is a function that's continuous on an interval from a to b, and there's a y value between f of a and f of b, then there is an x value c in the interval so that f of c is equal to y. We're not going to prove this theorem because it actually turns out it's pretty tricky to prove. But just to understand what this says, let's draw a picture of the whole situation. So we have a function, and it's continuous on the interval from a to b, so let me write a couple x values here. And remember, to draw a function that's continuous, I can't lift up my pencil as I draw this, so something like this. So there's a continuous function from a to b. And we have a y value that's between f of a and f of b. F of a, well, here's the point on the graph corresponding to a. So there's f of a. And the point on the graph corresponding to b is right here. And there's f of b. And we have some y value that's between f of a and f of b. So maybe y is right here. So this is the setup. This is the setup for the intermediate value theorem. And what the intermediate value theorem says is, down here on the x-axis between a and b, somewhere there's an x value that the function sends to y. We don't know where it is. The intermediate value doesn't tell you where it is. But there's guaranteed to be some x value down here that gets sent up to y. If you actually have a graph like this, you can sort of see where it has to be. You can go over to the graph and then down. And there's our x value c. So f of c is equal to y on this graph. Now the reason why it's continuity that makes this true is the following. Let's draw a graph. The same sort of situation, but I'll draw a graph that isn't continuous. So this graph has a jump discontinuity, like this. Okay, now we can mark f of a. F of a, it looks like it's about here. And f of b looks like it's about here. And this time for my y value, I'm going to put y right here. All right, so on this graph, is there any x value that gets sent to y? Well, let's see. All of these green x values, they all sort of hit this green part of the y-axis. Those are all too small. None of those take the value y. And as we move further to the right of this discontinuity, to these yellow x values, well, these yellow x values hit this upper part of the graph, and they all get sent to this yellow part of the y-axis. So none of these x values between a and b get sent to y. And you can see why that happens. It's because this graph jumped all the way across the value y, so that it never actually hits y. And of course, it's that jump that means this function isn't continuous. So that's why continuity is an important ingredient for the intermediate value theorem. The continuity forces the function to take on every value between f of a and f of b. So let's see how this gets used. Let's set a problem for ourselves. And the problem that we're going to attack is solving an equation. Let's solve this equation. 4x equals e to the x. Okay, well, I guess one thing you might try is, because there's an x up in the exponent here, you might try to solve this equation by taking a natural log on both sides. But if you take a natural log on both sides, you get natural log of 4x equals x. But now there's an x that's trapped inside a natural log. To get the x outside of this natural log, I guess you would exponentiate, But that would just take you back to the equation that you started with. But we decided that we couldn't solve that equation as it was. So we're kind of stuck here. We can't solve this equation because there's an x outside of the exponent and inside the exponent. Solving this exactly pretty much is not going to happen. But here's what we can do. One way to get this started is just to subtract 4x on both sides. We get 0 equals e to the x minus 4x. And then what we can do is name the left-hand side of this equation f of x. So let's say f of x is the function e to the x minus 4x. Okay. So we want to solve the equation f of x equals 0. Right? Because this line right here just says f of x equals 0. Okay, so that's the equation that we want to solve. And one thing to notice about this function f is that, well, exponentials are continuous, and this 4x is a line. Lines are continuous, and when you subtract continuous functions, you get a continuous function. So f of x is continuous wherever it's defined. Of course, it's defined for all real numbers, so f of x is continuous for all real numbers. Okay, that means if we set things up right, we can use the intermediate value theorem, because to use the intermediate value theorem, your function has to be continuous, and ours is. Okay, well, let's see. We can't solve the equation exactly, but what happens if we plug in, say, 0? F of 0 is, let's see, e to the 0 minus 4 times 0. That's 1, because e to the 0 is 1. And that's bigger than 0. 1 is definitely bigger than 0. All right, what about, I don't know, how about f of 1? That would be e to the 1 minus 4 times 1. And e to the 1, that's e. E is about, not exactly, but e is about 2.7. And so 2.7 minus 4, that's definitely negative. Okay, well, let's draw a picture of the situation so far. We don't know what the graph looks like, but we do know that at x equals 0, our function takes on the value 1. And at x equals 1, our function takes on some negative value. 2.7 minus 4, I guess, is about negative 1.3. So down here, maybe. Okay, notice that one of these values is greater than 0, and one of these values is less than 0. So by the intermediate value theorem, right, 0 is in between 1 and negative 1.3. And so the intermediate value theorem says there is an x value in the interval from minus 1.3 to, sorry, no. There is an x value in the interval from, in the interval 0 to 1, where our function f takes the value 0. But that would be a solution to the equation. So what the intermediate value theorem is saying is that there is a solution to our equation somewhere between x equals 0 and x equals 1. So before now, we didn't have any idea of where there might be a solution. But now we know there's a solution between 0 and 1. Okay, well, it's good to know that there's a solution between 0 and 1, but that doesn't tell us all that much about what the solution is. But here's what we can do. We know there's a solution somewhere between 0 and 1, so let's take this interval and cut it in half. That gives us x equals a half. And let's see what is f of a half. So this is e to the 1/2 minus 4 times x, which is 1/2. So this is the square root of e minus 4 times 1/2 is 2. And we need to get some idea of what this is. So square root of e, let's see, I've got a calculator here. I'm going to do e, and then take the square root of that, and then subtract 2. This is about negative 0.35. All right, so over on the graph, at 1/2, we get negative 0.35. So something like this. And that's less than 0. All right. Well, now think about using the intermediate value theorem again. To use the intermediate value theorem, the value we want, which is 0, needs to be between the y values we have. And the y values we have are 1 and negative 0.35. And negative 1.3, but 0 isn't between negative 1.3 and negative 0.35. So we don't want to use x equals 1/2 and x equals 1 because that doesn't include the y value we want. We should use x equals 0 and x equals 1/2 because the y value we want is between these two y values. So the y value we want is between f of 0 and f of 1/2. So the intermediate value theorem says there is a solution to our equation in the interval from 0 to 1/2. So you see, before now we knew there was a solution somewhere between 0 and 1, but now we know there's a solution between 0 and 1/2. So the size of the interval where we might have a solution is half as big. And we can repeat this whole process. So we can plug in a quarter. So let me do that. So I'm going to evaluate f of 1 over 4. That's e to the 1 over 4 minus 4 times 1 over 4. So I'm just plugging that into my calculator. And I've made a mistake because I got a negative number. There we go, minus 1. And this time I got 0.28. And that's bigger than 0. So that means I can put another point on this graph. At x equals 1 over 4, I get 0.28, so something like that. All right, now we know that between 1 over 4 and 1 over 2, there has to be a solution because at 1 over 4, the function is positive. At 1 over 2, the function is negative. So the intermediate value theorem says somewhere in between 1 over 4 and 1 over 2, the function has to be 0. So now we know there's a solution between 1 over 4 and 1 over 2. You can see if you look at the intervals we're getting, we started with from 0 to 1, and then from 0 to 1/2, and then from 1 over 4 to 1/2. Every time we do this subdivision process and use the intermediate value theorem, the size of the interval where we know there's a solution gets half as big. So if you wanted to get a really good idea of where a solution is, you could just repeat this process again and again. At every step, the interval is half as big, and eventually this interval is going to be very, very small. So if you have a solution that you can't solve exactly, and you want to find an approximate solution, you can repeatedly use the intermediate value theorem to subdivide an interval where there might be a solution until you have a really good idea of where the solution is.